Okay, thank you for the introduction and welcome to this talk here. I'm not sure if I can meet all his expectations, but what I thought is maybe I should do, it's a Saturday afternoon, I'll bring some nice pictures and we have some fun together. So what I'm talking about is the machine, the HPC system we have at the Leibniz Supercomputing Center, which is one of the 3 German national HPC centers. And in order to explain that, I would also need to kind of give a bit more details about the background. And what you see here on this picture is actually the Leibniz Supercomputing Center. It's these 5 buildings in front, which includes 2 institute buildings, which includes lecture halls also, and a visualization center, which we will also see in a second. The important part, of course, is this one over here, the twin cube, or the cuboid, as we say, which has 72 by 36 meters and 36 in height. And you also see on top already part of the equipment, which is all the cooling equipment. So if you take any of these boxes that you see in the left part of the picture, well, that's actually where each of these boxes cools 2.2 megawatts. So the interesting part is in the 5 floors below. So there's 1 floor with the HPC machine, 1 floor just servers. And interestingly enough, only 1/3 of the center is being used for the computers. The rest of the floors is needed to run these computers. And we talked about when we developed codes for these machines, and Mr. Cornelius also said I should give some explanations on what the challenges are. And we will see the challenge is not only the software, but is also how the software interacts with all these infrastructure parts. So if we are doing all these things, then we talk about our 200 people, which means about 2/3 of them are funded by the state of Bavaria, 1/3 is funded by research grants, and they are serving about 90,000 students. Well, actually, I heard at the moment it's already 100,000 students, and we have about 30,000 employees, including 8,500 scientists. And what we do is we provide not only HPC services, but we are basically the computer center for all the Munich universities. So we provide, as I always say, all the fun IT stuff. We don't do SAP, we don't do any controlling stuff, financial stuff. We do really the stuff that the scientist needs on his desktop. So what you see here in the picture is basically one thing we do is the Munich network, the research network, which is in total, just to give you one number, 4,600 kilometers of cables, which also connects to Germany's largest mountains, where there is a research station on top. The second role that we have is we are also kind of, whenever there is big stuff to be invested. That means whenever there is somebody in Bavaria, you need to buy a big cluster, or like what you see in this picture, the Virtual Reality and Visualization Center, you put it in one place, and at that one place you operate it for all of Bavaria, which means any scientist can use these capabilities. And then, as I mentioned before, we are also one of the national supercomputing centers. And in Germany we have 3 of them, which fit together under the umbrella called the GCS, the Gauss Center for Supercomputing, and which is actually the centers in Jülich, Stuttgart, and ourselves. And if we talk about that, basically that's the top of the pyramid we're talking about. That's the machine called SuperMUC. Those of you traveling with planes know that MUC is the acronym for Munich Airport, and SuperMUC is the machine that we are running. You also see on the pyramid that the rest of the building, of course, has a number of other systems, and in total we have at the moment for also 5 clusters. 1 is being renewed at this point. The interesting part for the Leibniz Supercomputing Center is that we're providing all this service on x86-based architectures. So from the desktop to the biggest machine, you have pure x86 to do all your computations. So let's go back to the national role as a supercomputing center, because that also connects to the European role, where we have basically scientists from all over Europe using the PRAISE infrastructure, the Partnership for Advanced Computing in Europe. And that is basically the vehicle for European scientists. You use cycles on our system. That always comes back to the question, how can we get access to the system? Well, you don't pay for it, or rather you pay with your good name. So a proposal for one of these machines always means you have to submit something which is scientifically excellent and which needs to fit to the architecture of the machine. And we'll see in a second what that also means. So let's go to the machine. You see it here in this picture. This is the top floor of the twin cubes, as I've shown you. And basically this is half of the room. About 600 square meters, which hosts this system, and as you see, each of these blocks, of course, is a rack with 2 meters in size, and on top of the racks you see the yellow stuff, which is the basic InfiniBand cabling. So in the architecture you will see later it's 18 islands, or rather 19 islands, which are connected by a fat tree, and this is basically resembled by what we see in yellow on top of it. The interesting part is also what you don't see, because it's the one in the double floor. The double floor for this machine is 1.80 meters, and as I always say, politically incorrect, we hire only people smaller than 1.80 so they can work easily down there. But of course the reason is we need the space. We used to need it for the machine that was air-cooled. Now we need it to put all the electricity and the water in the double floor. And that means you can safely go into this room and everything that is dangerous is basically below you. Now, this is actually not a picture. This is a rendering by the machine itself, because the angle would be too difficult to make a picture from up there. Anyway, the important thing for the politicians is, of course, where does this machine end up in the top 500 list? And as you see, I'm using a very outdated list here, the June 2012 list. And on that list, we have been position 4, which is the best ever position we had. And that's what the politicians understand. We will see later that reality is something different. And the number to look here is the second column from the right, which says 3,185. So 3.2 petaflops is the performance that is peak on this machine. Meaning, if all the processes run optimal and do only matrix multiplication, only multiplications actually, then you would get something like 3.2 petaflops. Actually, that comes at a cost, and you see the power consumption is 3.4 megawatts for that point in time. So to give you also a ballpark figure here, 1 hour of operation of the center costs 1,000 euros just in electricity. I always put this down for the scientists, saying, well, on one day we spend 25,000 euros just on electricity, and 3 days we spend one PhD student for a year. Or on the other way around, in 1 year we spend 120 PhD students just on electricity for this particular system. So puts it together also that you have here 147,000 cores. You see there's one island missing. We'll see that in a second, which means in total we have about 155,000 cores in that particular version of the system. Now that is also a continuation of a trend we have been following over the last years. And you see here, starting in 1990, we have always tried to follow this exponential curve of the exponential curve is an interesting statement. The curve, of course, for the performance increase. And you see, whenever there was a new machine, we basically tried to come close to the curve again. One interesting thing here is that the red gives you the performance, while yellow gives you the memory capacity. And you see we have there already a divergence, that the memory is not increasing at the same size. And for the developer, that means, of course, we are getting to a situation where the amount of memory per core does not increase at the same speed as the performance that you get from the core. And that has some effects if you think of it in terms of what you program these systems. Now, of course, this is not the last system, and as I said, this was 2012. So right now, or in June, we already put the SuperMOOC Phase 2 into operation. And you see it here on this picture. SuperMOOC Phase 2 is the 2 racks in front on the right side. And actually, these 2 racks, 3 years after the installation of the first phase, provide the same performance. So in total, we see here 230,000 x86 cores. You have in total, you would have a theoretical performance of 6.4 petaflops. And the interesting thing again is the new version 3 years later requires only 1/3 of the area and requires only 1/4 of the power consumption, which is an interesting development if you think of it. And you see the remaining space here is actually already in place for the next system to come somehow. So if we talk about all these systems, and what you saw there in value is basically a machine in total of 130 million euros, that needs to be spent well. Actually, we're spending on this application mix, and I think we have a wide application mix. In total, we have about 200 different applications, 200 groups which are using these systems as indicated before. And as you see from these characteristics, it's quite diverse groups also that are coming in. If I give you some numbers, we would say about 1/3 is physics, which means material physics, high energy physics, and astrophysics. 1/3 is about computational fluid dynamics, and the rest is distributed over the other areas. But of course, that is different from year to year. This is again just a number to have some idea. So here's one example I wanted to show you, which is an interesting example because it gives you also an indication what we get back as a value. As I said, we are not being paid. We get money for running this system, and the scientists use it for free. So if we talk about this particular application, you have the name down there, Alexandros Stamatakis from HITS in Heidelberg. He's using the system for finding out these phylogenetic tree computations. And what he does is actually he looks at the gene sequences and tries to identify the relationships between different animals. So in this kind, it's insect. We will also see later he had done the same for the birds. So the idea is you do some sequencing, you do some alignment, and afterwards you get a tree which kind of contains all the different variations of this genetic lineup, and then you see how these animals are connected together. Well, actually, if you just think the number of possible trees for 150 species, well, that's the number that you get out. So it's 4.22 times 10 by the power of 301. And that gives you an idea of the amount of computation you need to do this thing, to find out what the trees actually are. And actually, here you have some ideas. The project is called OneKite, so it gives you all this transcriptome evolution stuff. And you also have in the top right, in the bottom right corner, you have kind of this software tree, the data flow that is needed to do all that. So this is a big data and high performance computing application. It needs new software approaches. It also needs kind of improvements where you need tools, and that's where we want to get to, kind of where do you use all these tools that are around at the center and that Intel is providing for us. So he has been using these tools, and he made some interesting results with that. Like, for instance, just simple things like reading the data used to cost 15 minutes just to read all the data in. He didn't do any processing, yeah? But by kind of optimizing it, he got it down to 1 minute. Also, he got it down on 1,000 cores from 10 days to 17 hours. And then if you think back of what I said before, 1,000 euro per hour, well, actually, that's kind of an improvement which affects all the science on the machine, because other users can use now the remaining cycles for doing some important stuff. Load balancing is another thing where you need analysis tools to see where that fits in and how you can improve that. So here is what I promised. This is the result we get. But actually, he had 2 publications in Science, one on the birds and one on the insects. And that's the payback, more or less. He's doing excellent science by using the machine as good as possible. And if he does that with efficient code, it also means other scientists can use the remaining cycles efficiently for their work. So what we are looking for is really excellent science, but also good codes that use the machines with the optimal performance that we can get out of it. So let's go a little bit more in programming this system. And actually, one of the interesting observations is just take a look at the size of the system. This is the previous system. So this is a system that has 8 meters by 10 meters. And at that time, it was the most powerful system. When we upgraded that, we got to this system, which was an Itanium-based system. We said 11 by 22 meters. And the last one is 21 by 29 meters. So instead of the expected decrease in size, we have also always seen an increase in size. But what does that mean also for the user? I want to look into this with you. One of the effects is, of course, you have to kind of build a new building every time, which isn't scalable. Yeah? So we need to find a way on restricting that. Well, the restriction comes today if you think of power. At this point in time, we're starting to buy the machine for the amount of power we can afford to run it, which is strange. So you would not spend all the budget on the hardware. You would spend as much budget on the hardware as you can put up to run with the budget left for the energy, which is an interesting effect. And gets back to what I just said before with this example. The more energy efficient you run, the better it is also for the user kind of having a bigger system in that case. So here we see the construction of the building. But of course, the interesting part is also the architecture itself. So I mentioned we have 155,000 cores on SuperMOOC phase 1. This is just an architectural diagram of phase 1. So what we see is we have 18 SYN node islands and 1 FAT node island. And the difference here is in the amount of memory per core. So in the FAT node you have 6.4 gigabyte per core. In the SYN node you have 2 gigabyte per core. Yeah? What is the effect of that? The user needs to know actually how much memory is needed, and he needs to go to the right queue in order to submit his job. The other thing is, of course, you see the memory architecture in the background, Scratch and home directories, but also backup and archive, has an effect on that. Actually, these days we see many things coming, and I'll have an example on that one as well, from the file system. If you write millions of files, you easily crash the file system. Actually, if you write millions of files, it also has an effect on the power consumption of the system. And we have seen interesting effects of that as well. So the interesting part here is this is still pure x86. So there's no GPU, there is no accelerator in here. So think of the systems getting more and more complex. You would probably have also islands with different architectures in here, which again would have an effect on writing the software for the system. And I think here we need tools which are also kind of integrating the software development across all these different heterogeneous architectures. Actually, if we talk about the system that we are using, the software is already hybrid in a sense, because we are using MPI and OpenMP, at least for those codes which really scale well. If you use pure MPI, well, that's the most used programming model for most of the architectures. But the rest, as you see, is using a mixture of OpenMP and MPI. And those codes that really want to scale well have to use this mixture. And again, it's a burden on the developer to make sure that these things are being put up in the code, used efficiently to kind of run on these systems. Now the other thing here is, of course, if you take a look at the percentage of hybrid resource usage by research areas, you also see it depends on the developers. So obviously astrophysics is using quite a number of hybrid OpenMP and MPI codes. And actually, if you think about astrophysics, that's those guys who never have enough computing power. Yeah? They can spend whatever computing power you give them, they will be happy and spend it. Yeah? So they are using this already because they are scaling well. And then you see also the other areas where kind of more and more of this hybrid model is getting into operation. And here is another example that we see. Well, actually, where we need to think about is AVX and SIMD, of course. And we see also the distribution of where do the flops come from. And again, we put in another model, another level of heterogeneity, and we need to have software tools to kind of support that. Because here we see that 75 to 85% of all the flops we get from the application mix we have are coming from vectorization, which again has an effect, a strong effect on what you do with software development. The other effect we have, and we talked about that a little bit already, is the power consumption. So for us it's important, of course, how much money we spend on the power, and you see the curve is steadily going up. Well, actually, with one exception, in 2009 it got constant, which I would say didn't mean nobody worked at the center. It didn't mean we didn't buy any new machines. Actually, we bought new machines, but that's the effect of water cooling. We changed from air cooling to water cooling, so we stayed constant with the power, but had more performance in the center. And as you see, in 2012, the new machine came up, and it was 70 times more powerful than the previous HPC machine, but it used only 3 times more power for the computation, which is also a good effect. So at one point, you need to get rid of these big machines, because there's a new machine that gives you more power with much more performance with much less power. So the user also has to take control of that. What you see here is the water cooling. In SuperMOOC, we use warm water cooling. So we go in with water that is already at 36 degrees Celsius, and it comes out with 68 degrees Celsius. Well, why are we using warm water cooling? Because you have seen the chillers or the cooling equipment on the rooftop. All we need to do is to cool that down, is to transport it to the roof. And statistically, there's one day in Munich where it is above 36 degrees Celsius. Well, this year we had a bit more of these days, so it again meant we had more power consumption also for the cooling. But in principle, this is a very efficient and power-efficient cooling mechanism for the system. Why is this important for the user? Well, actually what we need to do is we need to run the codes of the users with the optimal clock frequency. And the optimal clock frequency is not always the full clock frequency that you get from the processor, but actually it's the clock frequency that fits best to your application. And the more memory accesses you have in there, as a rule of thumb, the more you can go down with the clock frequency. And the more you go down, the more energy you save, and other people are able to use the performance of the system. So that puts it in together with all these factors. And here is just a little table which shows you the development of the last few machines. And of course, the last column on the right side gives you the number of cores. So the number of cores is only one aspect which is interesting for the code developer of these systems. All these other aspects that I've been mentioning need to be taken into consideration as well. Now I want to go with you a little bit more into this number of cores per application. And these two diagrams give you the number of cores used actually in the applications on both phases of SuperMOOC. Left side is SuperMOOC, the synth nodes from phase 1. Right side is SuperMOOC, the new Haswell nodes on phase 2. And you see there that the applications are running quite with a number of different core numbers. So we see 29% on Haswell is running with 8,000 to 16,000 cores. Yeah? The other ones, smaller, 28 is running with 4,000 to 8,000 cores. So this is the average range kind of where your application is. So most of the users are doing that. The question is, of course, why would you spend on a system that has 155,000 or 230,000 cores if most of the applications run in that mode? Well, actually, we built the system up specifically for the big codes. So we need to have a mechanism to get the users who can use hundreds of thousands of cores for their applications to run their codes and to get their codes, first of all, being scalable, to go up to that level. And we are doing that with a thing that we call the Extreme Scale Workshop. So the idea was you need an incentive. The user kind of likes to do the things he did yesterday. Yeah? So we need to kind of find ideas of how we get them up. So that was an effect. We did the first workshop we did already in 2013. And at that point, we invited 15 projects. And the prerequisite was basically you had to run on 32,000 cores. If you were running on 32,000 cores and these software codes, the numbers, the names you see here, were basically running on 32,000 cores, and we said if you can double the number of cores in your code, then we declare success. And that means for the scientists, they get a publication and free access to one of these conferences. So the idea really is we give them an incentive to do this. And then we were sitting together with them and working on that. Now, one of the things is in regular operations, they get only 4 islands. So they get a maximum of 32,000 cores. And they have to do it in batch processing. Yeah? So for this workshop, we gave the course to them interactively, and they had it reserved for 2.5 days. So they could run any code up to 100,000 cores in these 2.5 days. Well, actually, we were using only 16 islands. And I'll give you the maths a little bit later. 16 islands of the system for also reliability. If there's a problem, we could switch over to one of the other islands. And in total, they were able to consume in 1 hour 130,000 CPU hours, which actually means in total they could consume in this 2.5 days the allocation they usually get in 1 year. So I believe that was the real incentive. You know, you're not computed towards your real allocation, you get some extra hours, which is a 1 year in total what you have on the system usually. So here is the results table, and that gives you some ideas. So in the first column you have the name of the code, which you see, first line up there is LINPACK, which is this benchmark that we have been using for top 500. And for LINPACK on 128,000 cores, we see last column, the right column, we see 2,560 teraflops, which means 2.5, 2.6 petaflops, which is close to the peak performance of that systems with 16 islands with 128,000 cores. So that's what LINPACK gives you. The problem is, of course, all the rows below that give you reality. And as you see, reality is quite different from what you see with LINPACK. The best code, which is Vertex from Plasma Physics, gets about 10% of what you get with LINPACK on that system. That is not a bad code. In contrast, that's a very good code. But it still delivers only 10% of the peak performance. try to explain that to any of the politicians around, you know. That's the real issue here, yeah? But for the developer, of course, it is a success if you get that amount of performance out of your code. Actually, take a look at the fourth line, which is Sysol, which is seismic code. And actually, you see there are 95 teraflops on a configuration with 64,000 cores. Well, actually, we'll get back to that, yeah? But you see that this code is still not bad. It gets only 5% of the total performance available. But I want you to keep this number in the back of your mind, and we'll see that a little bit later again. Now, actually, if we take a look at the performance on SuperMOOC, including the idling nodes, then we also see that, well, the average, it says mittlere Performance, so we have the German term here. The average performance is actually not bad, but it's of course far away from the 3 petaflops we have. Yeah? So reality is you get about 10% out of that. And you actually get that because we're mixing big applications and small applications. Yeah? So there's one thing already in there, which means also the floating point performance is 5 to 8% of peak, what we see on these systems. And then of course, take a look at these results of this workshop. So we see what we had for each of this code. We had lovely scaling curves. Yeah? So you see you increase the number of cores and you get wonderful scaling on the codes that we have there. Not unexpected. But of course it's now up to the users to generate the data that could scale with the number of cores up there. So this is one of the results. More interesting for us is of course the lessons learned. So the aspects that we got out of the development of the codes on these big size systems. One of them is, in this first workshop, we learned that MPI plus OpenMP was slower, but was better scaling. That is surprising, actually. You wouldn't expect that. And actually, we found out that there is a configuration problem there. And we saw during the development after this workshop that now MPI and OpenMP is faster than pure MPI and scaling better. But that was really something which we had to learn because we had these users going this extra step. We also had things with core pinning, which was difficult, and we only managed to do that because Intel was in the house and helped us kind of making sure that we used this efficiently. And as you see, the last 2 points here already indicate we had some difficulties with the file I/O. And again, that helped us to fine-tune the system and see how we could improve it. Now the idea is also, what do you do with this knowledge? One of the things is we take these codes and we have a benchmark suite for the procurement, for instance, of the next system, but also for testing other systems of other centers. And that's available in public, so anybody could download that. In addition, all these users who put in this extra effort have now the opportunity to run their code on the full system. And actually, at the moment, we have 14 codes on both phases which use the entire machine. And they can run it on the entire machine always after maintenance, because that's when the machine is empty and they can just do some production runs. And we repeated the workshop again in June 2014. And you see, we really had some valuable results again. And we learned some new things again in the development. The idea is really you sit together in a room with your people until white smoke comes out of the chimney, more or less. Yeah? So you have some learning effects on both sides, not only the developers, but also the people that run the codes. And we increased that and did this extreme scale-out SuperMOOC Phase 2, which actually means when we bought SuperMOOC Phase 2, or when we put it into operation, we used 30 days, 1 month of the entire system just to do large-scale runs. Yeah? So that really means that these early users, this selected group, had the possibility, had 63 million core hours available to do their production runs on the system, and they used almost 70% out of that for real large-scale core runs. And that was also an interesting experience because for us, we learned if the system is stable, was one aspect, but also how the software works with scalability going up to that level. So the other thing here is, again, some software development things. Well, we learned that those teams succeeded that had the best preparation. Well, that's something that my mother always said somehow, yeah? Comes back again when you're working professionally. Heisenbugs, the effects that you see certain bugs only at certain levels of the execution, race conditions, these kinds of things came up. MPI is getting to a limit when we get to these levels and there's also one discussion going on here on what we can do there. And we learned that hybrid is, of course, the way to go. And we come back to what I said before, that it's really now the better solution. Now, the other thing we learned, of course, is you need this more individualized services for the users. And if I talk about users here, I mean the actually developers. So you sit together with them. And so we identified 4 areas, which is astrophysics, energy, life science, and environmental computing. And we put for those 4 areas, we have specialized group which sit together with the developers, and together they are working on these new codes. For us, it is also important to kind of work on equal footing, meaning that the computer scientist is treated as a partner, not just as an outsider running the system, but you're more working closely together with the applied sciences. And then, of course, for us it helps to understand what the needs of the users are much more clearly. So we also get feedback on procuring the next system by seeing what they want. Yeah? Often you get your users, they come in and say, we need GPUs. But in fact, when you sit down with them, you see they don't need GPUs, they need good file I/O, whatever. Yeah? Just to give one example. And that helps if you work closely together. And here's an example from environmental computing why we focused on that. What you see here is Europe and the Mediterranean, and the red area is where flooding occurred during this time frame from 1978 to 1994. Well, actually, we had a series of projects already, and you see also there is quite some damage going on. In that case, in this time frame, for 16 years, where 29 billion euros in damages were produced by floods. And by kind of improving the codes, and we did that, for instance, for this flooding that occurred in Genoa in 2008 and 2011, we were able to go down to new levels of granularity and precision, and we were able to suddenly have simulations that were able to predict the flooding that occurred. And in Genoa, it killed 17 people, so we could have, if there would be the right policy, have an idea already what would have happened, which nobody ever saw because they were not able to compute with that granularity. So putting that together means also we need to put that into the lectures, and this is one of the lectures we have on parallel computing that's going on at the University of Munich. And there we also see you have to kind of do this again for shared memory systems, for distributed memory systems, and then also for data parallelism as we have it in here. So it's always a cycle. And here again we have been collaborating, and Mr. Cornelius was so kind to also give a talk to the students from the side of Intel. And this is also an idea of where you get more knowledge about running these complex systems to the users. Now let's talk one slide about what we are using, the tools from Intel at the center. You see we have all these compilers, we have the performance libraries, we use them for our daily work, and of course we have all these analysis tools which help you to understand what's going on. There's also an interesting development that we're basically learning with these extreme scale workshops what information we need, and that goes back again to the software developers, and we try to also improve on that with respect to what the next capability, the next functionality of the software is. And then, of course, one thing is the cluster toolkit. So Intel MPI, there was a discussion where also developers were interested to use our system, scaling up to numbers which not that many systems have around in number of cores. But of course, we all know that the next system may have 800,000 cores, may have 1 million cores. Yeah? And then you would need a software library that scales up to that. And we do some more even. Yeah? One of the things is we have this dedicated documentation. We have this partnership initiative. We have the web pages for the developers. We have tutorials and courses that go on. So you need to do this. You need to help them. And as I said, the better we are with terms from energy to solution with the scientific results, the more scientists we can support on our system. And then I just learned when preparing that talk that there will be a workshop next week on HPC code modernization going on, which is at the center and is again one of the collaborations we have. So let me come back to the example we had in the table. Remember, we had the SISOL code, which is a seismic simulation, which, as we know, predicting earthquakes is not possible, but at least it helps you to have a simulation to understand what's going on during an earthquake and how the earthquake kind of travels through the hull of the planet. Now we had, if you remember, 95 teraflops on 64,000 cores. Well, we sat down after this workshop with the users and worked with them. Actually, the work was done by a group of Michael Bader, who is a computer scientist, and together with Christian Peltis, who is the environmental scientist. And they improved the code. And they ended up getting 1.4 petaflops on the 3 petaflop machine. So that means we got again up from the 95 teraflops on half of the machine to 1.4 petaflops on the full machine. And I would consider that world record in terms of what you get out of performance on these large-scale machines. That's a real number. That's not LINPACK. That's something that you get for production runs with this code. Actually, what you see in the background is one of these volcanoes where there was an earthquake down there, and they wanted to understand how the eruption goes down through the hull of the planet. And that was only possible by having all this performance available. So this is really a result of software development and kind of using the machine as good as possible. And that's what we have now in performance. So we get this in production runs. So getting to the conclusions. Well, we see the complexity is increasing. Not only the extreme scale, the number of cores is one issue. And we need that the software tools follow these number of cores. But what we also see is the complexity of the system in general, like in heterogeneity, is increasing. Yeah? You may not have, we don't know what the next system is now, yeah? But it may not be a pure x86 system. It may have other elements in there as well. Maybe some for big data, maybe some accelerators, maybe some GPUs. Yeah? There will be a procurement process just for us, which will find that out. So we need to have a means of handling this complexity. And that can only work if we have the tools to handle that, more or less. The other thing is, of course, that the users need the possibility to run their codes on the full machine. So we still need the big machines where they have 100,000, a million cores, because there are applications which only get to a level of granularity and a resolution which you can only get if you have these machines. So there needs to be also the possibility to run that, and you need to have that on the full-size machines. We found that this extreme scale workshop, which I introduced a little bit to you, is a good incentive for the users, and we are repeating that. So there's already a date for next year, and if you would have an application that you would be interested in, also data you would be interested, there is a possibility to participate in that. You would find that out by Googling for the Extreme Scaling Workshop at LRC next year. And then, of course, as I said, the most valuable thing is not that we got out these codes. That's one good benefit. But very valuable is also the knowledge you gain from that. It's like, what is the input? What were the problems? Where could we improve? And it helps us in operating the center, running the system, making sure the next users are doing that. If you want to know more about that, well, there is this partnership initiative, PyCS as we call it, and actually, which is interesting because it's a challenge to publish a paper about such a process, that was being accepted at one of the conferences, and the paper is can be downloaded as open access. And with that, I'm at the end of the talk. I think that was exactly the time that we agreed upon. And you see a last picture here. I should also mention there is a number of people who contributed slides to that. Yeah? Which means I was late in preparing the slides because they didn't deliver. Yeah? It's not my fault, of course. Yeah? But on the other hand, I'm glad that all these people helped in preparing this talk. So if you have any questions, I'll be happy to answer them.